Hey guys, okay, we're going to get started with our respiratory system lecture. I'm going to go fast, and so just pause it if you need to stop to write something down. All right, first of all, the 4 parts of breathing. So we're going to go through all 4 parts. The first part is called ventilation. You might have heard a lot in the news about ventilators right now, and so this is the picture of a man on a ventilator. The idea of ventilation is just getting air in and out of the lungs. So we're just trying to actually get air in, so basically breathing in and out. So we've got a ventilator over here in the corner. And that's just the machine that would do it for you. So if you're no longer able to breathe on your own, we would have a ventilator that could do that for you until you're able to. So it's a machine that helps somebody breathe. The thing about being on a ventilator is you can see it goes right down their mouth, past their pharynx, down into their trachea, which goes into their lungs. So it's going to be going right through here, down into the trachea, and into the lung. But the thing about that is that you are not able to eat or speak if you're on a ventilator because it's bypassing your vocal cords, which are right about here. And the air is not actually passing over your vocal cords because the air is going down the tube. And so nothing is actually hitting the vocal cords. And you're also not able to eat because remember that our mouth also leads past the pharynx into the esophagus, which runs just a little bit posterior to your trachea. And you would not be able to eat. You would have to be probably have some kind of feeding tube. All right, the next kind of respiration, we have 4 parts. We had ventilation, is external respiration. External respiration is going to be between our alveoli, which are in our lungs, and that's the final part of the lungs, and our blood. This is a little bit tricky because a lot of people get confused with the term external, but with external respiration, it's not actually breathing in and out. Remember, that was ventilation. This is just the oxygen and the carbon dioxide moving between the alveoli in our lungs and the blood in our bloodstream. So let's write a couple of things down. So the oxygen is picked up by blood. And then the CO2 goes into the alveoli. Okay. Gases always move from high to low concentration. You might remember that from freshman year when we talked about osmosis and diffusion. So they're always going to move from high to low concentrations. So in our lungs, when we breathe in, we would have a lot of oxygen, and this is our lung area in here, the alveoli. Okay, so you would have a large concentration of oxygen. And then in our capillaries, we're going to have more CO2. So you'll see that here and here. So things are always going to move from high to low. So you see the CO2 moving into the alveoli, and the oxygen moving into the red blood cells. All right, so just in general for gas transport, we want to know how this oxygen and carbon dioxide moves in our body. So oxygen is going to be carried by the blood, and so is CO2. So they're both going to be carried by the blood. Okay. Specifically, oxygen is carried by hemoglobin. We'll talk a little bit about that in just a second. The carbon dioxide is going to generally, about 98% of it, I think, carried in the plasma. We'll talk about that in just a second as well. So hemoglobin is located on our red blood cells. You have 4 hemoglobins. There's one here, one here, one here, and one here. Each hemoglobin can attach, it has iron, which attaches and is attractive to oxygen. So each hemoglobin can carry up to 4 oxygens. And we actually have, this is going to be crazy, more than 280 million hemoglobins. But not in our body. We have over 280 million hemoglobins in each red blood cell. So if you add like all the red blood cells that we have, I think it's something like 20 trillion. 20 trillion red blood cells times 280 million hemoglobins times 4 oxygens each. It's going to be like quadrillions and quadrillions and quadrillions of oxygens that could be carried. But remember, oxygen is super important. Oxygen is what gives us energy. So we need a lot of oxygens to keep ourselves alive. And so it's going to be super important that we can have a lot of oxygens being carried all the time in our blood. All right, internal respiration is going to be the next type of respiration. So we did ventilation. Remember, that was just breathing in and out. Then we did external respiration, which is kind of named oddly, but external respiration is the oxygen and CO2 moving between our alveoli and our lungs. So this is going to be oxygen and CO2 moving also, but now this time it's going to be between our blood, which is now where the two things are being carried, and our tissue cells. A tissue cell can be anything, a skin cell, a muscle cell, a brain cell, a heart muscle cell, a kidney cell. Any cell in your body needs oxygen, and it needs to get rid of CO2. So oxygen is going to go into the tissues. And the CO2 is going to move into the blood. Remember, into the plasma. The plasma is the liquid area of the blood. Most CO2 is carried in the plasma. And it's carried as something called bicarbonate. Bicarbonate is what happens when CO2 and water combine. It forms a compound called HCO3, and it's slightly acidic. And so that's why your pH, which is what measures your blood acidity, it has to be a certain amount, because if it goes off of that, you have too much CO2 in your blood and it gets too acidic, then it can be very dangerous and your tissues can start dying. So if you take a look at the picture, we're going to see that the CO2, remember this is a tissue cell over here, and then this is the red blood cell over here. The CO2 is going to be moving from our cells. Our cells are constantly making CO2 as a byproduct, but it's toxic, so we have to get rid of it. So it's going to be moving out of the tissue cells, and it's going to be moving into the plasma in the bloodstream. And then the oxygen is going to be moving in the opposite direction. The oxygen is going to be moving from the red blood cells, okay, over here, and into the tissues, because the tissues need oxygen to keep going through cellular respiration to keep you alive. All right, respiratory system in general. We know the 4 ways that we're getting oxygen into our tissue cells and the ways that we're getting carbon dioxide out of our tissues and out of our body so we can breathe it out. The respiratory system is really good at this, and there's some different things that make it really good at this. And those things that make it really good at diffusion is that it has a really thin surface. If you think about it, the cells are only, it's only 1 layer thick. So it's simple squamous. So those cells are really thin and remember really flat. You just have 1 layer of cells and they're really flat. So oxygen and CO2 can move really easily. If you had a wall that was really thin, you'd be able to hear things on each side of the wall. Just like in the classroom, sometimes we can hear the classroom next door. But if you built a really thick wall, if you had multiple layers of cells, then you're not going to be able to hear things in the other room. You're not going to be able to move things across. So being thin and flat make it super good at diffusion. The next thing that makes it really good at diffusion is that it's slightly moist. Gases move better when they're dissolved in water. So the fact that there's water in our respiratory system and that it's moist, you can see your breath sometimes and you can fog up a mirror or a window, you know that there's a little bit of water there. Also being warm, your capillaries, which are your blood vessels, are running underneath the surface of all of these areas. If you've ever had scraped the inside of your nose or the inside of your mouth, you know that it can bleed pretty easily. And that's because there's a lot of blood vessels right under the surface. So those blood vessels are warming the air as it passes by. And then the final and possibly the most important thing, especially if you watch the crash course, they're going to talk about this a lot. We talked about surface area a lot when we were doing digestive system. Having a large surface area is going to be really important. In the alveoli, the walls of the alveoli bubble out, and so you get lots of surface area for oxygen and CO2 to be moving across. Lots of area for that to be doing that. All right, inspiration versus expiration. So inspiration is going to be breathing in. Expiration is going to be moving out. In inspiration, we're going to increase the size of our chest. Remember, that's called our thoracic cavity. We're going to be increasing the volume in our lungs. So you're going to be giving it more space. Because it has more space, that's going to lower the pressure in your lungs. And then things always move from high pressure to low pressure. So if the lungs have lower pressure, the outside air then therefore has higher pressure. So air from the outside is going to rush in to your lungs and basically creates what they call a vacuum. Not like a vacuum where you would be cleaning, but a vacuum where there's a lower pressure in one area and a higher pressure in the other. Expiration is the exact opposite. So you're going to decrease the size of your chest cavity. You're going to decrease the volume in your lungs. There's going to be less space. This is going to raise the pressure in your lungs. And then things always move from high pressure to low pressure. So air is going to move. That's an M. Let me erase that. That's terrible. It's hard to write on this app. Air moves in. Air moves out of the lungs. There we go. All right. Let's see what we have next. Okay, so we have just a picture showing the diaphragm. That's the muscle that we talked about. It's a smooth muscle. Your brain has control over it. The diaphragm's right here. And it's basically this dome-shaped muscle at the lower part of your rib cage, lower part of your lungs. And as it moves up or down, it's going to change the size of your lungs. So here you can see it's moving downwards, which makes the lungs expand. You get more volume, less pressure, so air is going to move in. As the diaphragm moves up, it's pushing up, that squishes your lungs. So that you can see that this purple area, there's a lot less area here. And then that's going to decrease the area, which increases the pressure, and then air gets pushed out. All right, everything is controlled by the brain. You do not have to think about it. It's a process that is automatic. Your brain does it on its own. You certainly could think about breathing, and you could concentrate on it and control your breathing to a certain extent, but your brain has total control over it. And that's why if you're not thinking about it, or you're sleeping, for example, you are still breathing. So the two parts of the brain, which are near the brainstem, which is the bottom of the brain, are the medulla oblongata, which is kind of this area. Notice it also in the brain, there's lots of wrinkles with lots of surface area. And then the pons area of the brainstem. Things that can affect your breathing. Overdoses, and that's why it's so dangerous. If you have an overdose of drugs or of alcohol, those things can impair your brainstem's activity. So overdoses of drugs and alcohol can impair, or the fancy word they use is suppress. That means like to stop these areas of the brain. And so sometimes you will stop breathing if you have an overdose, and that could be what causes death eventually. Another thing that drugs can do is they can slow it down. They can cause irregular breathing, where like you're not breathing in the normal pattern. And it may stop altogether, as we just talked about. Okay. All right, things that can affect your breathing rate. So there's lots of things. One is volition, and this is like just a fancy word that they use. And volition is your conscious control. We were just talking about that, how you can think about your breathing, and you do have some conscious control over breathing. But remember, it is limited. If you decide to hold your breath, that's fine. But eventually the body, or the brain, I should say, will take over. So if you hold your breath, you can actually hold your breath so long and you'll pass out, and then your brain takes over and it just starts breathing again. It sends the message for you to breathe again. Other things that can affect your breathing rate is your physical actions at that time. If you're talking, that might affect your breathing. If you're coughing, that might affect your breathing. If you're exercising. If you're nervous, that's on the next page actually, and then your lungs themselves. So the physical condition of your lungs. Some people have conditions where their lungs lose their elasticity, which is just a fancy way of saying how stretchy your lungs are. We do have a certain amount that our lungs will expand, but there's a limit. We don't want overinflation. We don't want our lungs to just keep breathing in as much as possible, because that would be dangerous. So we want to prevent overinflation of our lungs. And so there's a certain stretchiness, and then it stops. All right, I was just talking a little bit about nervousness and things like that. So emotional factors can also play a role in your breathing rate. One of the things could be fear, if you're scared, if you're nervous, if you're in pain. Those can all change the rate of your breathing. Body chemicals, those are usually talking about things inside the body, and that's mainly what I was talking about a few slides ago, which is our levels of carbon dioxide. If you have a high level of carbon dioxide, so if you were like working out, for example, you might increase your carbon dioxide. Your brain then increases your breathing rate to try to get rid of it. We don't want to have too much of it. We want to stay in homeostasis. All right, pathway of air into your lungs. All right, the first thing that it's going to hit is either your mouth or your nose, depending on what you're breathing through. Your nose is probably going to be a better thing to do. When we this first started with the COVID, we talked about a lot in the news, breathing through your nose, trying to make a conscious effort. There's a couple things that are in your mouth and nose, and one of those things is mucus, and the mucus is sticky, and so that's going to moisten the air because it's wet. And another thing it does is it traps any bad guy. A bad guy is called a pathogen. So that could be a virus, a bacteria, dirt, dust, whatever. Other things besides mucus is nose hairs. Your mouth obviously doesn't have that. So your nose has two pathways. Your nose, one, has more mucus. Your mouth has actually a little bit of mucus and then the saliva, but your nose has more mucus. And so the nose is going to be the preferred method in terms of your immune system for you to breathe, so that you can get all of the nose hairs and the mucus to be trapping the pathogens. The second part that the air moves through is the pharynx. The pharynx is basically the connection point between your nose and your mouth right here. So you can actually cough, and you can have food or liquids go up into your nasal cavity and come out your nose. If you've ever been choking or coughing or laughing too much while you're eating, you might have like water come out your nose. I had a friend who could take a chain and he would pass the chain into his mouth, like a necklace you'd wear around your neck, and then he would dangle it in the back, and then he would cough. And this weird cough, I should say that again. He would put the chain up his nose, tilt his head back, and dangle it down so that it went and snaked back into his nose. He would cough, and then he would reach into his mouth, and as he coughed, the chain flapped forwards, and then he would reach into his mouth and grab it, and then he would link it, and then he would pull on it. It was disgusting. It's a crazy party trick. I wouldn't suggest it, but you can have that all linked together. All right, so the pharynx is actually a spot for air and food. Remember, your food goes past the pharynx too. But what it has for the respiratory system is it has mucus, and it has, similar to nose hairs, it has cilia. And both of those things do the same thing they did earlier. Remember, the mucus is going to moisten, and it's going to also, everything is getting warmed. We'll add that. But it moistens, and it traps the pathogen. So the mucus, remember, moistens, and then the cilia traps. Another thing that's happening throughout all of this is the air is getting warmed. So I'm just going to list it one more time, and then we're going to assume it happens every time. Moistens, warms, and traps. Moistens, warms, and traps. All right, now we're going to move past the epiglottis. It's this little flap. When you're swallowing, it closes, and so it actually covers your trachea if you're swallowing, because we want the food to go down our esophagus. We don't want it to go into our trachea. So it's this little flap, and I'll kind of draw a little picture here, which is right about here. Oops, let me go here. Okay, just above the larynx, and it would close over your trachea, and then the food would move into the back, into the second tube, which is the esophagus. The next part is going to be the larynx. The larynx also is going to be now the pathway into the trachea. So this is going to be air only, or should be air only. If food goes this way or drinks, liquids, that's when you're going to choke. So you're going to feel that urge to cough to get it up. The air is going to move through here, and there's going to be mucus and cilia. And remember, mucus and cilia, every time, they're going to moisten, warm, and trap. So I'm not going to write it every time, but we're going to assume that we know that every time we see mucus, it's moistening and warming. And every time we see cilia, it's trapping the bad guys. All right, the next place that we're going to pass by is the trachea. Oops, let me do that again. Again, the trachea should be air only. And again, if you get food or drink down there, that's when you're going to choke. It has, surprise, surprise, mucus and cilia. Next up is the bronchi. You have two, a left bronchus and a right bronchus. And the bronchi, you can see labeled over here, are going to be also lined with mucus and cilia. So we're still warming, moistening, and trapping the bad guys, anything that we don't want to get into our lungs. We want to protect our lungs. The bronchi branch into even smaller passageways called bronchioles. So you can see those. And the bronchioles, I'm going to label some of them, would be here, and here, and here, and here, and here. And I'll just do them all in yellow. So they're all the offshoots, all the branches coming off of the bronchi. And so these are going to be smaller passageways for air, still have the mucus and the cilia, which is warming, moistening, and trapping the bad guys. And then finally at the end, we have the alveoli. The alveoli are all those little bubbles that you see. So you're going to see all these little bubbles. I'm just going to make little dots over them. And they bubble out. They look like little clusters of grapes. I'm going to draw it over here maybe so you can see zoomed in. So from the bronchiole out to these bubbly alveoli. And that is the only spot where there is not mucus and cilia. We want it to be really one cell thick, so these all have simple squamous. We want it to be free of the mucus and free of the cilia so that there's a large surface area. And that's going to be for all of the gas exchange, for all of the diffusion of gases. And those gases, remember, that are important are the oxygen and CO2 moving back and forth. And these alveoli are surrounded by your blood capillaries, which is where the oxygen and the CO2 are being carried. So, just to review, everywhere along the way, there's mucus and cilia, 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 mucus and cilia. Okay, let me see here. I've got them all labeled. Good. Mucus, cilia, everywhere, 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 except for alveoli. The mucus and cilia and also the blood vessels are warming, moistening, and trapping the air. All right. Nothing on this one. This is just a picture showing a zoom in of the alveoli, and this is a great picture because you can see all of the blood vessels, the capillaries surrounding it. All right. These two slides, you can just take a look at them, read through them, nothing much to say there. And then we have all the different conditions. I'm going to stop it there. You can read through the conditions on your own using the answer key to the notes. There's not a whole lot that I want to talk about. I might do one more video at a later date, which is going to discuss some of these conditions, but we can talk about those later on, maybe next week. So that is all for now.